Alright, so we're going to be doing some kinematic problems, and you typically see this in Physics 1. And there are certain equations that we use when we have situations dealing with kinematics. And there's four main ones that we use, and they're used to find position and velocity, mainly. And you can rearrange them to find time, acceleration, etc. But the main four that we're looking at is to find the final position of an object. You have x naught plus v naught times t. To find the final velocity, you have v naught plus a times t, where a is acceleration and t is time. The final position is equal to x naught plus v naught t plus 1/2 at squared. And the final velocity squared equals v naught squared plus 2a delta x. And the naught notation just means initial. So you can replace this with i's if you think that's better for you. But the naught notation just means initial. So an example that I'm going to work out is a stone is dropped into a deep well and is heard hitting the water 3.41 seconds after being dropped. How deep is this well? So I'm going to erase this to give myself some room. But the first thing that you want to look for when you hear how deep is something or how far did something go, you usually want to start looking at your position equations because you're dealing with distance here. You're not necessarily trying to find the speed of that rock that was dropped or stone. You want to find the position. So in this case, analyzing it, think about what you have. You have the initial position, x naught. So let me draw a little diagram. So we have a well here. This is the start of the well. And it goes down some distance, which we're trying to find. And it hits the water here. So we have a stone falling down. And somebody drops a stone from this height right here. We can call this height x naught. Okay. And when it hits the water, that is our final height because it's asking how deep is the well. And when it says how deep is the well, it's not talking about the whole well itself. It just means when does this stone hit the water from its beginning height. Okay, so we know that this stone is dropped. So if something is dropped and not given any initial push to get it going, we know that the initial velocity of that object, in this case the stone, the initial velocity of that object is just going to be 0 meters per second. Okay, so now we already have v naught, we have x naught, and our final x. So in the problem, it gives us t already. It said that the stone is dropped, and then 3.41 seconds later, it hits the water. Okay, so we're given t. So in this case, we want to use this equation because since it's in free fall, we know that it has an acceleration downwards. If we were to use this equation, we wouldn't have an a to work with. Here, if we use this equation, we have an acceleration to work with. And in this case, since the stone is in free fall, there's no other forces acting on it, the acceleration is simply the acceleration due to gravity, which is just negative g, which is just negative 9.81 meters per second. And I'm using the negative here to denote direction. Since it's going down, I'm going to call it down negative. So I'll write that up here. Down is negative. Okay, which is why I have negative 9.8. Alright, so I'm just going to write this equation right here. So we have x final equals x naught plus v naught t plus 1/2 at squared. Okay, so using the information we're given, we have all these variables. We have x naught, which here is we can define this height here to be height 0. We can say that this is 0, because that's where our stone is beginning to be dropped. So that means that our x naught is equal to 0 meters, okay? Because we can define at what height we want to start counting from. So our x naught is 0, so we have x naught, okay? V naught, remember it's dropped, so that's going to be 0 meters per second. So in this, we can call this 0. 0 times time is just going to be 0. So all we're left with is 1/2 AT squared. And we can't make that 0 because time's not 0 and A is not 0. We're given this here, T and A. So our final position is just simply going to be 1/2 AT squared. And this is a pretty common case. If you're dropping an object from a certain height, you're giving it no initial velocity, you're just dropping it from a height and let it go into free fall. If you want to find out how far it travels, you just use this. And although I'm writing an x here, it applies in the y direction as well. You could write final y if you wanted to, but I'm just writing x for the time being. So, given the variables that we've already found and the time that the problem has given us, we can say that the final position is just going to be 1/2. Our A here is negative g, which is negative 9.81 meters per second. So we have 1/2 negative 9.81 meters per second squared, times t squared. So we have 3.41 seconds squared. Okay. So when we work this out, we're going to have that x final equals negative 9.81 meters per second squared over 2 times 11.63. When we take 3.41 squared, we get 11.63, and our seconds become squared as well. Okay, so what I can do here is these seconds squared cancel out with these seconds squared, because seconds squared here is in the denominator. Seconds multiplied by